Alright, so this is video number 11, lecture video 11 for math 5500 regression 1. Okay, so in our previous lecture, lecture 10, we discussed about the confidence interval. Okay, confidence interval for the mean. Confidence interval for the mean. When sigma is given, we used to use G critical. When sigma is not given, we used to use T critical. And then we did the confidence interval for the proportion, where we need to check n times p greater than 10, right? That requirement need to be checked. After that, we did the confidence interval for the difference. I want to tell a little bit about that. This is my lecture note that I used. Okay, this is the page I was there. In my previous lecture, I was little incomplete about this in terms of the data. N1 is equal to 45, N2 is equal to 40. This is the height of football players, and this one is for the height of basketball players. Okay, N1 is equal to 45, N2 is equal to 40, but the data is not given here. Okay, so for this problem, you need the data. Okay, so I'll show you how to use that data to find the first sample mean, second sample mean, the sample standard deviation for those two samples. Okay, I'll show how to do this one. Let's go there. So I'll go to R. I'm here in R. Okay, my data should be here. This is exactly what I put in Blackboard. Okay, so let's go to R. Okay, this football is the data for the height of professional football players. Okay, nothing comes up, this is good. And this is the height of basketball players. Okay, so this is the first data and this is the second data. Okay, so let's find the mean now. Mean football, this gives you x1 bar. Okay, so this gives you x1 bar, and then I'll find the other one, mean basketball. This gives the mean height of basketball players. Okay, so the football players, the mean height was 6.17. Basketball players, the mean height was 6.45. Okay, the standard deviation of football players, this will give you. Okay, this is the standard deviation of football players. And then you do the standard deviation of basketball players. Basketball. This gives the standard deviation of basketball players. Okay, so this is x1 bar, this is x2 bar, this is s1, the standard deviation of football players, s2, the standard deviation of basketball players' height. Okay, this is the height data. Okay, in feet. So I got x1 bar, x2 bar, s1, s2. So I'll go to the slides now. This is how I got x1 bar, x2 bar, s1 and s2, right? Once you got that, I need to find the confidence interval. Okay, so you need to check the requirement. The requirements meet because the sample size is 45 here, the sample size is 40 here. Okay, so the central limit theorem will work here. Okay, how do you find the confidence interval? I'll give you a little idea about that. So we got x1 bar, we got x2 bar, we got s1, we got s2, we got from the data, from R, right here, x1 bar, x2 bar, s1, s2. This is how it is. Okay, so the confidence interval formula will be x1 bar minus x2 bar plus minus t critical, and then standard deviation 1 squared divided by n1, the standard deviation 2 squared divided by n2. This is the formula. x1 bar, x2 bar we have here, right? s1 we have here, s2 I have here, n1 is right here 45, n2 is right here 40. And then the question comes, what is t critical? So you need the smaller, like here I have 40 and here is I have 45. So the smaller one is 40. 40 minus 1 is 39. Okay, whenever you go to the chart, you need to go for the 39 degrees of freedom and 90%. Okay, so the 90% confidence interval and 39 degrees of freedom. I will show you how to get that. I'll go to my table right here. So 39, right? So I need to go to 39. 39 is not here. So if what you are looking for is not there, you need to go to the closest one but below, not up. Okay, so 39 is what you are looking for. 39 is not there, so you'll use 40. No, you have to go down. Okay, so whatever you need is not there, you always go down. So 39 is what you need, it's not there, you have to use 35. Use this row, you need to use this row now, 35. And then 90% is right here, so the value should be in this column, right? 90%, so this should be the one, right? 1.690, because I need 39. 39 is not there, so closest one but down. So I got 35, that is 1.690 for 90% confidence interval. So once again, 1.690, yes. So my t critical is equal to 1.690. I could not find 39, so I have to go for 35, right? All right, so this is how you get. So you'll get the confidence interval. And does the interval consist of all positive, all negative, or different signs? Okay, both plus, both are positive, both are negative, one is negative, one is positive. You have to answer that. Okay, if you will get this thing, that means mu1 minus mu2. If mu1 minus mu2 is positive, that means mu1 is greater than mu2, right? If mu1 minus mu2 is negative, then mu1 is smaller than mu2. If one is negative and then one is positive, we cannot say which one is greater, right? So you need to answer that. Which distribution did you use? Did you use T or the standard normal? Standard normal is G or T. I use T because sigma 1, sigma 2 are unknown. Okay, since sigma 1, sigma 2 are unknown, we used T critical, T distribution, right? The data set I told you in, this is in Blackboard, right? The answers are right here. So I just did once, so double check your answers. If the answers are incorrect, tell me. Okay, I have one more practice problem for you. If you want to do the data set feet length in week 4 folder in Blackboard has the length in centimeter of feet of 20 fourth grader students in a school. Okay, so understand, there are 20 students, those are from the 4th grade in a school, and we got the data for their feet length to determine what number shoe size do they need. Okay, to figure out the size of the shoe they wear, we went and then we did the measurement of the length of feet of the kids in fourth grade. Okay, we have 20 kids, so you need to find the 99% confidence interval for the true length of all fourth graders feet. Interpret this. Okay, you need to find the confidence interval and then you need to do the interpretation. Finding the confidence interval, in this case the formula will be x bar plus minus t critical s divided by n. X bar is in the data, s is in the data, right? N you can count. Oh yeah, I have n is equal to 20, so you need t 19 degrees of freedom for what percentage? 99%, right? There is something I wanted to tell you. I will show you how the data looks like. The data is right here. Okay, feet length. This is the data. Okay, this is the data I have put in Blackboard. Remember, the problem here does not tell you that the data is normal. The normal distribution is not stored here. Okay, the population is not normal. The question does not say the population is normal. The sample size is small. In this case, you need to check that if there are outliers or not. How the data is. Does the data come from normal population? We don't know. So you need to check the data if the data has any outliers. Understand this, what I am telling here. The population is not normal. The sample size is small, then smaller than 30. So we have to check the normality of the data. Okay, we need to check for this problem, we need to check the normality of the data. Okay, we need to check the normality and we need to see if the data has any outliers. Okay, that is what we need to check. How do you do that? I want to show you a little bit. Okay, this is my data. So basic R course foot length. To save time, I have written my R commands already here. So I'll go to R. Alright, so I set my working directory, the one you have seen before, right? Nothing comes up, good. I need to read the data. Okay, so I read the data. The name of the data is foot length .csv. This is the CSV format. Attach the data. You know that if I don't attach, I cannot see. Okay, so let's see how the data looks like. Okay, see, the data is like right here, only one column. This is size of the shoes, size of the feet of the kids in the fourth grade, right? So in centimeter, I guess. Let me double check. Yes, in centimeter. Okay, so in the fourth grade, the kids, there are 20 kids, their feet length in centimeter given here. The problem does not say the data is, the population is normal and we have the sample size small. So you need to check the normality now. Okay, so how do you check the normality? I'll tell you here what I'm trying to do. We need to check and see if there are any outliers. Okay, so if there are any severe extreme outliers, then the conditions do not meet, we should not find the confidence interval. Okay, so let's see. There is a way for checking the normality and then checking for outliers, that is called QQ plot. Okay, that is called QQ plot. Some people call it normal probability plot. Okay, some people call it QQ plot, that means quantile plot. Some people call it normal probability plot. Okay, so what is that? So the command for that plot is QQ norm. Okay, QQ plot used for testing the normality. So QQ norm, the name of my variable is size right here. I want a red color. See, this is called QQ plot. This says here normal quantile plot. Okay, let me do QQ line, one more command that will draw straight line pretty much on the diagonal. So how do you interpret this plot? What happens is, if there are some outliers, then the data will be something like here or here, like that. Okay, here all the points are very close to this straight line. Okay, all these points are very close to the straight line. That means the normality assumption is satisfied. Once again, the normality assumption is satisfactory here because all the points are very close to the straight line. That's one thing. There are no outliers. If the outliers are there, this point would be somewhere here or here, like that. Okay, so this is pretty good plot. And if you need to copy and then paste this plot in your document, right click in it, copy as bitmap, and then go ahead and then put in your, see, this is how it is. Okay, just paste this. So the conditions in this slide, it doesn't say the normal population, it doesn't have bigger sample size. So in that case, you need to check the normality. We check the normality, no outliers, and then pretty normal, right? So if you need the commands for how to get this normal probability plot, see, okay, the commands are right here. You can pause this video and look at it. Okay, pretty simple, straightforward. This is already with you, so all you need is, this is not the command, so these two lines only. Okay, only these two lines are needed for getting the plot. This size is the name of the variable. You need to change the name of the variable, that is size here. Okay, you need to change this if you have different data, otherwise this is how it works. Okay, all right, so we did this. So I'm done with this confidence interval chapter for mean. So all we did was we did the confidence interval for mean. So now we will go ahead and then do the hypothesis testing. Okay, so let's go ahead for the hypothesis testing. I assume you have done pretty much this part in your high school, basic stats class, and then I want to recall a little bit. Okay, hypothesis testing. Recall, there are the three possible forms for the hypothesis for a test of mean. Okay, mean mu. One is called left tail, one is right tail, and then one is two tail. HO, that is called the null hypothesis. H1, that is called the alternate hypothesis. The null hypothesis and the alternate hypothesis. You are familiar with this thing, right? Left tail, this is less symbol, LL. Left tail and then less, LL, right? That works here. Right tail, this is greater. Okay, so the null hypothesis is always the same. mu is equal to some given value, that is the null hypothesis everywhere. The alternate hypothesis, left tail, this is less than, right tail, this is greater, okay, and then two tail, this is not equal to, okay. So this is the basic revision from your basic stats class, okay. Equal sign, symbol is equal sign, is has stayed the same, that is for the null hypothesis, okay. Not equal, this one is different from, has changed from, differs from. So I'll show you where to use this chart. In your hypothesis testing problems, the problem says the different from, that means this, has changed from, this means this, or differs from, this is what it is, okay. Sorry. Sorry. Oh no, sorry about that. And then here was some problem in the PowerPoint slide I gave you, that is less than, this less symbol. If there is a greater than, there would be greater symbol. Less than is used when the problem says is below, is smaller than, or has decreased. If the problem says these things, that means less than, okay. This thing I'll again explain in coming slides. All right, hypothesis testing. So even in graduate classes, people mess up how to write down the null and alternate hypothesis. I want to tell you that to you. Remember, this mu is the population mean, this is the parameter, okay. X bar is the sample mean, this is the statistic, okay. So mu is the parameter, X bar is the statistic. When you are doing the hypothesis testing for mean, always you have to use mu, okay, for the hypothesis. When you do your null and alternate hypothesis, always use this population mean, not the sample mean X bar. Remember, in your null hypothesis and alternate hypothesis, this never comes. Always comes this population mean, okay. Suppose you want to test a claim that the population mean is 40. So the population mean is mu is 40. State the null hypothesis. The null hypothesis is HO, okay. So HO, the population mean is mu is equal to 40. This is how you write down. You never write down X bar is equal to 40. Here is, I'm telling you population mean, so you write down mu. If it says just mean, not the population mean, mean only, still you do mu, not X bar here. That's one very important part. State the alternate hypothesis. The alternate hypothesis is H1, okay. If you have no information on how the population mean might differ, that means if there is the key differ, then you will do mu, same mu here, same 40 here. When this says differ, this symbol comes. Let me show you once again. Did you see here? If I tell you somewhere differs, has changed, or different, if this kind of key are given, that means use this symbol. See, I told you different from, changed from, or differs from. In this case, this is the symbol that you use, okay. So that's what I'm applying here. See, differ from, so I used this one. State the alternate hypothesis, okay. Another H1. The population mean is mu. See, exceed means more, right? So exceed means greater, sorry, not 20, 40. Sorry about that. And one more example here. State the alternate hypothesis if you believe from experience or past knowledge that the population mean may be less. I told you here, see, less, this is the one. Okay, so let me go here. The population mean is like S1. The population mean is mu less than 40. Remember, this is H1 and this is mu. I should be writing in this way, but I just do this. Okay, don't be confused. This is mu. Mu means the population mean. Okay, remember, if somebody writes x bar is equal to 40 as the null hypothesis, this is wrong. The null hypothesis or the alternate hypothesis, this x bar should not be there. There should be mu. Okay, that should be population parameter. So that should be population mean, not the sample mean x bar. So for the null hypothesis and the alternate hypothesis. Okay, so I'm asking very basic question here. There are 4 examples. You pause the video now. Okay, please pause the video right now and answer these 4 questions where there are mistakes. Okay, explain whether the following hypotheses are in valid form or not. Check it. Where the mistakes are, you need to correct it. Okay, so you understand how to write down the null hypothesis, alternate hypothesis or not. You need to check that. Okay, please pause this video and then check where are the mistakes, correct the mistakes, and then you check my answers. Okay, so my answers will follow now. Okay, the null hypothesis x bar is equal to 60. This is not correct. So the null hypothesis can have never that x bar. There should be, this should be the null hypothesis mu is equal to 60. Okay, so here is x bar. The x bar should not be here. In place of x bar, there should be mu. Okay, x bar is also mean, mu is also mean, but this is what we need. The null hypothesis, alternate hypothesis, always the population parameter, not the statistic. Okay, same way, is not equal to 60, that works. H1 is fine, but this x bar again should be mu is not equal to 60, that is H1. Okay, so this should not be x bar, this should be mu not equal to 60. This is how you write down. Okay, the null hypothesis mu is equal to 100, that's absolutely fine, and this is fine as well. The population mean is, this is less than 100, that's absolutely fine. Okay, the null hypothesis population parameter mu, that's good, number is here. Remember, the null hypothesis always comes this equality sign, less cannot be there. Okay, so this one, the null hypothesis is mu is equal to 12. This is the problem here. Sorry. Remember, the null hypothesis cannot have this sign. There should be is equal to sign. Okay, not this greater sign. This should be equality sign. Okay, and this, the alternate hypothesis is equal to, it never works. The alternate hypothesis, this guy should be either less or it could be greater, it could be not equal to, but is equal to does not work here. Okay, that's how it is. Mu is equal to 8, and then okay, here is a problem. Mu is equal to 18 here, mu is not equal to, that's okay. This number should be the same here. Here is 18, this should be 18 as well, or this should be 22 and then this should be 22. This number right here and this number should match. Like here 60 and then 60 match, good. 100 match, good. 12 match good, but here is 18 and here is 22. That should match. Okay, so that's what it is. So let me write down one example. HO mu is equal to 100. H1 mu is less than 100. This is from here. This is correct. Sometimes people write down in this form is equal to sign. Sometimes people write down, if you understand this, this is absolutely correct. This is enough for you to understand. Some people do, see, here is less, so they will do greater equal to. Some people do in this way as well. If you have seen this before, then yes, this is also fine. But if you have not seen this before, don't be confused. What you do is, null hypothesis mu is equal to 100. The alternate hypothesis mu is less than 100. That's what you need to understand. Do not worry about this. Again, the null hypothesis has this sign. The alternate has this or this or this. Okay, any one of these. That is how you write down the null hypothesis and the alternate hypothesis. And again, remember, the null hypothesis and the alternate hypothesis always has the population parameter, not the statistic. Okay, once again, when you go to the regression chapter, maybe next week, when you do the hypothesis testing, always there should be the population parameter, not the statistic. Remember this thing. You need that concept for the regression as well. Okay. Okay. We did the confidence interval when sigma is known as well as when sigma is unknown. Okay. We did the confidence interval for those two cases, sigma known, sigma unknown. Same thing is here. Hypothesis test of mean when x is normal and then sigma is known. If sigma is known, we have to use g. Okay, g is equal to, it's not very clear, this should be x bar right here. Okay, g is equal to x bar minus mu divided by sigma divided by square root of n. So this is what the formula for g is. Okay, and in the sample size, mu is the population mean, right? The value is stated in the null. That's okay. So I should fill up here. This is called p-value. Okay, p-value, I think I will explain the p-value when I go to the example, but let me read a little bit here. Assuming the null hypothesis is true, what is the p-value? P-value is the probability. Okay, this p is the probability value, the probability that the test statistic will take on values as extreme or more extreme than the observed test statistic. Okay, so what does this really mean? I'll show you in example. So the test statistic will take on values as extreme or more extreme than the observed test statistic. What does this mean? I'll show you. Okay, I think I'll tell you that right here. You will be using the test statistic, either G or T. G is used if sigma is known, and then T is used if sigma is unknown. If sigma is given to you, we have to go to G. Sigma is unknown, sigma is not given to you, you have to go to T. Okay, so for now sigma is given, so assume we have G. Then the p-value means the probability. See, the p-value is the probability p that the test statistic is G will take on values extreme or more extreme, as extreme or more extreme than the observed test statistic. So from the data you will calculate this observed test statistic, that is denoted by G, I don't know, CAL, G calculated. Once again, assuming the null hypothesis is true, in that condition, what is p-value? P-value is the probability here that the test statistic, that test statistic means G, okay, will take on values extreme or more extreme than the observed test statistic. This observed test statistic is GCAL, means G calculated, okay, G calculated. Extreme means in this place here could be sometime less, could be sometime greater, okay, that is what that extreme is trying to tell you. In this place there is sometime less, sometime greater, depending on, once again, in this place there is either less or greater. How do you know this is less or this is greater? If the alternate hypothesis is less, then there will be less here as well. If the alternate hypothesis is greater, this will be greater as well. Once again, the sign, the equality sign that comes here depends on the alternate hypothesis. If the alternate hypothesis has less, this will be less as well. If the alternate hypothesis has greater, then this will be greater. So that is why I told you I'll show you this thing in next slide as well, okay. I'll spend pretty significant amount of time for explaining this p-value, okay. I'll explain this again, this p-value part I'll explain again. So a larger p-value greater than 0.05, for example, indicates the results that were obtained would not be very surprising. What that means is, if the p-value is small, if the p-value is low, the null hypothesis go. That means whenever the p-value is smaller than this number, we reject the null hypothesis. If the p-value is smaller than alpha, we reject the null hypothesis, okay. That is what this tries to say, but I'll tell all this again later. I need this a lot when I go to regression, but for now I will tell you there is one case, the murder trial. The null hypothesis is the person is innocent, okay. Whenever somebody is involved in the murder case, the murder trial, the null hypothesis, before investigation they assume the person is innocent, that is the null hypothesis, and the alternate hypothesis is the person is guilty, okay. So there are two possibilities. The person is innocent, okay, the person is innocent and the person is found not guilty, okay, that is the correct decision. Yes, right, the person is innocent and he is found not guilty. That's pretty good, right? This is good. The person is guilty and the person is found guilty. That is good as well. If somebody is guilty and that person is found guilty as well, that is the correct decision. However, there are some problematic cases. The person is innocent, okay, has not done the crime, right, and that person is found guilty. That is called the type 1 error. Once again, the person is innocent and that person is found guilty. That is called type 1 error. The other thing is, the person is guilty and the person is found not guilty. Yes, he has done the crime, but it is found that he has not done the crime. That becomes the type 2 error, okay. All right, type 1 error the symbol is alpha. Okay. Type 2 error, the symbol is beta. Okay. And then this guy is the correct decision, here is 1 minus beta, and then this is the correct decision, this is 1 minus alpha. And notice this thing, this guy and then this guy, if you add, that becomes 1, that is the total probability. Same thing here, if you add this and this, that gives you 1, that means the total probability, right? All right. In this example, which one is more serious? Which error is more serious? Type 1 error, the person is innocent, we find the person is innocent and then we found guilty. Okay, the person is innocent and still that person we find guilty, that's type 1. Is that serious? Or the person is guilty, we found not guilty, is that serious? Which one do you think? Okay, so which error is more serious? Okay, think about this, and if you get confused, please let me know. I'm asking your opinion, which one is correct? Okay, and if you want to check the answer you got is correct or not, you can email me, I can tell you. Okay, okay, so there are two kind of errors. Okay, one is type 1 error, let me write down that here. Type 1 error, type 1 error is reject the null hypothesis when the null hypothesis is true. Remember, if the null hypothesis is true and then we reject it, that is called the type 1 error. Okay, and then type 2 error is fail to reject the null hypothesis when the alternate hypothesis is true, that means the null hypothesis is false. Okay, the null hypothesis is false, we should reject, but we fail to reject, that is called the type 2 error. Okay, so type 1 and then type 2 error, these are the ways that could be interpreted. Okay, so this is type 1 error and then this is type 2 error. The type 1 error, the symbol is alpha. Alpha is the probability of rejecting the null hypothesis when it is true, and it is the probability of a type 1 error. Okay, and then you go here, type 2 error. Type 2 error is the symbol beta, right? Type 1 error is alpha, type 2 error is beta, right? So let's go there. Type 2 error is beta. The probability of failing to reject the null hypothesis when it is false, that is called beta or the type 2 error. This is the probability of a type 2 error. Okay, this is type 1 error and this is type 2 error. Okay, alpha and beta both are set low, usually between 0.01 or 0.05. Sometimes people do 0.1. Okay, the alpha as well as beta both are chosen very small, and power of the test will come again in maybe next lectures. Alpha and beta are chosen as low as like 0.01 or 0.05. The power of the test increases as alpha increases. Okay, in other words, when alpha increases, beta decreases. That means these two probabilities are inversely related. One increases, the other decreases. Okay, That is the main thing. So I think we'll discuss more in the coming slide. The p-value, mainly the p-value, we'll discuss more in coming slides. Now let's go. This critical value method, this hypothesis testing, one is the critical value method, one is the p-value method. If the p-value is smaller than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. So in our example, I will not be using this. Okay, I will not be using this critical value method. I will be using this p-value method. I will find the p-value and I will compare the p-value with alpha, and if the p-value is smaller than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. Okay, so this is the way we use this concept. We rarely use this concept. Okay, all right, so we have time. I'll go ahead and then do one example for you. Okay, all right, so how to do the hypothesis testing, I want to tell you here. Let's do one example. Remember, whenever you are doing the hypothesis testing, you need to make sure that you check the requirement. You check the requirement means that, sorry, there is a problem. Yes, we got it. When you check the requirement, you need to check the conditions for the central limit theorem hold or not. Let me write down that here. In confidence interval or hypothesis testing, always check the requirements. Remember this thing, this is very important. Whenever you do the confidence interval or the hypothesis testing, you need to make sure you check the requirement. Requirement, what is that? That is, either the population should be normal. Note down if you need this. The requirement, either the population should be normal. If not, the sample size should be greater than 30. Population should be normal. If not, the sample size should be greater than 30. Okay, that requirement should meet. All right. 1 2 3 4 5 6 7 8. So looks like we have n is equal to 8 here, right? You read the story, all that. X bar is this. All right. So this is the hypothesis testing problem. First of all, you need to check sigma is given or not. Sigma is given, so we have to use G. Okay, all right. So in the beginning, you will write down the null hypothesis. The first step is writing the hypothesis. The null hypothesis is always the parameter. Parameter is equal to mean is equal to, what is mu is equal to right here? Okay, so 85 mg, that's per 100 ml, that's the unit, so don't worry. Mu is equal to 85, that is the null hypothesis. The alternate hypothesis is mu is the same, 85 is the same. Here is something. What is that? Do you see the key point? Higher. Always the null hypothesis is HO, this mu, the population parameter, is equal to whatever is given here. That's the null hypothesis. The alternate hypothesis is the same as this one here, same number here. This becomes different sign, and this is coming from the problem, this higher. Okay, that is the null hypothesis and the alternate hypothesis. That's step 1. Step 2 is alpha. What is alpha given? 0.0 0.05. Okay, the third thing is find the test statistic. That could be either G or that could be T, one of these, either G or T. How do you know this is G or T? Depending on sigma is given or not. Sigma is given, we do G. Okay, the formula for G is x bar minus mu. Okay, G is equal to x bar minus mu divided by sigma divided by square root of n. All right, x bar. What is x bar? It is given here. 93.8 minus mu is 85 divided by sigma. All right, what is sigma? Sigma is 12.5 divided by the square root of n. What is n? N is 8, right? All right. This calculation I will go ahead and then do in R. Okay, 93.8 minus 85. I'll go here. 93.8 minus 85 divided by sigma is, how much is sigma again? Sigma is 12.5 divided by square root, right, of square root of what? Let's see, n is 8, right? Okay, this is 1.99. Okay, if you round to 2 decimal places, G comes 1.99. Okay, so I got here G is equal to 1.99. Okay, so I need to discuss more. So if you need to copy this thing, you pause the video now and write down. Okay, this is the null hypothesis. The alternate hypothesis, alpha is equal to 0.05. the test statistic is G. I write down this as GCAL, that is G calculated. Okay, this means the G calculated. All right, the next thing is I need to find the p-value. How do I find the p-value? I will take these things off now. I wrote here 1.99. Did you see? I wrote here 1.99, and then yeah, I was giving the answer G is equal to 1.99. The same thing I got, right? All right, so let me take these things off. All right, the next thing I should do now is finding the p-value. Okay, so remember, the p-value is the probability. Always p-value is the probability. The test statistic will be here. This will be either G or T. In our case, G. Remember, the p-value is the probability that the test statistic could be either G or T. As extreme or more extreme than the observed value of the statistic. So the observed value of the statistic is G calculated. Always this rule works. The p-value is the probability that the test statistic G, and then G calculated here, and over here the sign is coming from the problem. The problem is saying higher. This is how you calculate the p-value. Okay, I think this should be clear now. The p-value is the probability that the test statistic is as extreme or more extreme. More extreme means that could be extreme, or more extreme means could be less, could be greater, depending on the problem. Okay, this is greater here. More extreme than the observed value of test statistic, that means G calculated. Okay, all right, G is greater than G calculated is 1.99. Okay, we are almost done, because this case, how to handle this case, we already did like last week, right? G is greater than 1.99. Greater means that is always you have to do 1 minus, right? And then what do you do? Go to the chart with 1.99, right? Go to the G chart with 1.99. How do you do that? Let me go to the G chart with 1.99. .99 is 9767. 9767. So right, so I'll go ahead and then do in R. One minus 9767, that is 0.0233, right? The p value comes is equal to 0.0233, right? That is the p value. It is always recommended to draw the picture. This is G chart. This is the standard normal curve. Okay, this is the mean 0. So G is greater than 1.99. You know that 1.99 is somewhere here, right? And then greater means here. This is the p value. Okay, this is the p value. This area is the p value. Okay, so the next thing is the conclusion. So p value is 0.0233. that's what I gave, right? The answer, we got the same thing. So the p value is this, and alpha is equal to 0.05. You compare, is the p value smaller or bigger? The p value is smaller than alpha, right? That means we always remember, when the p value is small, we reject the null hypothesis. We reject the null hypothesis at 5% significant level. Okay, we reject the null hypothesis at 5% significant level, because p value is smaller than alpha. I told you earlier, whenever the p value is smaller than alpha, we reject the null hypothesis. Okay, so the null hypothesis is rejected. I'll tell you what my null hypothesis was. Okay, so the null hypothesis was S naught mu is equal to 85. The alternate hypothesis was mu is, so this is rejected. That means we have enough, we have evidence, we have the proof that this is greater. Okay, we got the evidence that the mean is greater than 85. Okay, this is what we come up with here. Okay, so this is how it is. The hypothesis testing, this is not all. I will do this kind of examples, many more. That way you should be confident. Okay, if there is any part you are confused, send me an email. Otherwise I will do very similar one, more problem in the next, like video lecture 12. This is video lecture 11, and in video lecture 12 I will do more. Okay, thank you very much. This is all for now. Thank you.